Hello, everybody. This is a meeting of Math 111 where we are going over the solutions to the section 6.4 DA. So I'm going to share my screen. And we'll pull up the HTML of the solutions, which are over in the old DAs worked by Dr. White. So I've got them already up. Here they are. So the first one, the two categorical variables we were interested in was the sex of the student and how much they use sunscreen. So sex and sunscreen, they were out of that Youth Risk 03 data set. Previously, we'd way back in chapter 1, we'd looked at the relationship between sex and it was relationship between how much you use sunscreen and what your grades were. But we just did it in a descriptive way. But now we're going to study the relationship between two categorical variables using our full inferential powers in the chi-square test. So starting off with a simple tally table, you find there's roughly the same number of males and females in the overall sample. Sample size is about the same. And so when you see 700 males versus only 527 females never using sunscreen, or when you see 64 females versus only 27 males always using sunscreen, then you kind of think that this might give some indication that females are more inclined to use sunscreen. Of course, to nail that down better, you would want a table of column percents instead of just counts. But still, that's just what's in the samples from these two populations of all female high schoolers and all male high schoolers, is just the sample. Does the sample provide strong evidence that out there in the population, all high school students, of all high school students, that sex and sunscreen use are related? And the word feeling is in there. That is wrong. That's a typo. So I should really correct it. In fact, I'll correct it later. So anyway, you set up the hypotheses the usual way. The null says that the two variables are not related, that they're independent. Always will say that. And the alternative will disagree. And you just had to fill in the template to get the chi-square test running. And so twiddles the explanatory variable plus the response variable. I was thinking of sex as the explanatory variable here and sunscreen as the response. If you switched it around, it actually makes no difference in terms of what the value of the chi-square statistic is, or its degrees of freedom, or what the p-value is. It won't make any difference to your conclusions. But if you put the explanatory first, then some of the tables they show down here are just going to be easier for people to interpret. So looking at the observed counts, this is just a repeat of that tally table, except that we've arranged it to go in another direction. And then if the two variables are unrelated, what kind of counts would you expect to see in the table if you took this sample, of what was it, 1,422 females and 1,513 males? What would you expect to see in the table? And you would expect to see these counts, give or take some for chance error. And so there's some comparisons there that you would like to make just to sort of see if it looks like there's big differences. And then here, each of these numbers is the fraction of the chi-square statistic that comes from each count. And so like this 8.08 is the difference between the 527 and the 596 squared and then divided by the 596, and it came out to 8. And so you can see that the differences were kind of like most striking here and here and here and here. which kind of backs up what we saw when we originally looked at this table. We were kind of looking for some striking differences, and we found them there. Anyway, they also give the chi-square statistic, the degrees of freedom, and the p-value. And they're, with this graph, they're reminding you that they're approximating the p-value by looking at the area underneath the chi-square curve with 4 degrees of freedom. 4 degrees of freedom because it's rows minus 1 times columns minus 1. So rows is 2, columns is 5. 2 minus 1 times 5 minus 1 is 4. Okay. So the area underneath that curve passed 50.59, and that area is pretty small. So for the first question, the main complaint I had is that people were not very specific in their answers. So it says, compare the table of observed counts with the table of counts that would be expected if the two variables are independent. Comment on any outstanding differences you see. And then there's that second question. So when you do the comparison, you look for big differences, differences that look like they're striking. So like the 527 versus the 596, that looks like a big difference. The 380 versus the 389 does not look like that big a difference. The way you can really tell if a difference is big is by looking at the contribution of the chi-square statistic that goes with it. And so the differences that I would be inclined to talk about would be like any of these 4 that I've just selected. So I just picked a couple to mention. So there are several large and important differences between the observed and expected counts. For example, the null hypothesis expected this many females to never use sunscreen, but we observed only 527 doing so. The null also expected this many males to never use sunscreen. We observed only this many. So I kind of concentrated on the differences that were, in the never part. I could have just as well have concentrated on the differences that were in the always part. And I could have done both. There's actually a flaw in my answer, and maybe y'all can see it. It looks like I never actually said which of the two sexes appear to be less interested in using sunscreen. But based on the differences I've got here, it looks like the males are less interested in using sunscreen because the null was, expecting only this many to never use sunscreen, but more than that many were actually never using sunscreen. So I should fix that and post the fix. So let's see, the next question, if the null is right, what's the expected value of the chi-square statistic and what's the actual value? The expected value of the chi-square statistic is the degrees of freedom, 4. But it was actually 50, way more than the null would expect. So you can already tell it's looking really bad for the null. Next question is about the p-value. If the null is correct, what's the probability of getting a chi-square statistic at least as big as the one you actually got? Well, that's 0%, the p-value. Well, not exactly 0%, but a very, very small number that rounded down to 0%. And some people pointed that out in their answer, which was great. Should we reject the null? Kind of heading on now to the conclude step. Should we reject the null? Yeah, it's because it's less than 0.05. And then here's a step that a lot of people are still skipping. It says also write a simple conclusion. So you need a conclusion without any math in it that just says how strong the evidence is in your data for the alternative hypothesis. Well, here the data provides really strong evidence that out there in the population of all high school students, sex and use of sunscreen are related. Notice that that conclusion has no math. Doesn't talk about p-values, doesn't talk about null and alternative hypothesis, doesn't talk about chi-square stats, just talks about strength of evidence for the alternative spelled out in nice, simple words. Okay, so that kind of problem is easy enough to get all the parts right because like each question corresponds to one of the laid out steps in the logic of a test of hypothesis. And so a lot of people got this fine. Next up, sex and feeling about weight. So in the M111 survey data set, there was the variable sex, and there was also the weight feel variable, nice little ordinal categorical variable. And are they related out there in the Georgetown College population? Because when you tally up and make a two-way table for the response variable, how you feel about your weight, conditioned on the explanatory variable sex, it does kind of look like males are more likely to think that they're underweight. You know, it looks like 8 out of 31. That's about a fourth of the males think they're underweight. But look at that, only 1 out of 40 females thought they were underweight. And you could say similar things about the overweight row. But that's just the data. Is it strong evidence that out in the population, the two sexes feel differently about weight? So set up your null that says the two variables are independent and the alternative that says they're related. And head to the usual template. And I'm going to do twiddle sex plus weight feel, and everybody else did the same because sex feels like an explanatory variable here, so they put it first. And you get all this output. And most people just ran with that output. And in fact, I think everybody except one person in all of my 2 classes, so it's like over 40 people, everybody except this one person used this output. But look at that. There is a warning. It says some expected cell counts are low. The approximation of the p-value, this little approximation here, may be unreliable. This approximation got by using a chi-square curve with 2 degrees of freedom and looking for the area underneath it past your test statistic may be unreliable. Consider using simulation. So it's telling you this. And so you have to go back and like look in the slides like, okay, how do we do simulation? And what you do is you add simulate.p-value is true. And then you say how many times you want to simulate, and several thousand times will be fine. I think the person who got it right did it 10,000 times. And so then you get this different output, which has the same information about the observed counts, the same information about the count expected by the null, same contributions to the chi-square statistic, and same chi-square statistics, same degrees of freedom. But the p-value is gotten by doing the following thing 3,000 times. Go back into to 2 populations that you set up so that the 2 variables are not related, so that the 2 sexes feel the same about how they feel about the weight. Sample 40 females and 31 males. Make a 2-way table, make the chi-square statistic, keep a note of it, and then find out what percentage of those chi-square statistics got higher than the 14.6 that we actually got in our sample. And here is a little histogram of those 3,000 resampled chi-square statistics. Hardly any of them got past the 14.6. The rectangle that tries to cover them is so short, it can't even be seen it's different from the x-axis. And so now you can go and do your work. So the expected versus the observed, just like before, you look for some big differences and talk about them. And so, so I got my observed here, and I've got my expected here. So I might, for example, focus on the difference between the 5 females expected to say underweight versus the 1 that was expected to say underweight. I could similarly focus on the 8 males observed to say underweight versus the only 3.93 that were expected to say underweight. I would tend to focus on ones that deliver the largest contributions to the chi-square statistic to talk about them. If the null is right, what's the expected value of the chi-square statistic? That's the 2 degrees of freedom. What's the actual value? 14.6, and so way, way above what's expected. What's the chance of getting 14.6 or more if the null is right? That's your p-value. So when I ran this on my 3000 simulations, I got that value. If you did it with your simulations, you would get some other value, but it would be really small. So should we reject the null? Oh, yes, we should. The p-value is way less than 0.05. Simple conclusion, the data provides strong evidence that at Georgetown College, so talk about the population there, males and females differ in how they feel about their weight. And there you go. So a lot of people were just like totally fine on everything about it, except they just blew by the need to do simulation. So watch your output. It does check for you right there. And so it will draw your attention to the fact that some of the cell counts, this one right here in particular, are less than 5. And so that you might need to do simulation to get a better approximation to the p-value than what those chi-square curves would deliver for such small sample sizes.
Can you explain again really quickly how you do that?
How we do the simulation?
Yes.
Okay, so you take the same code, but you add 2 things to it. First, the command to please use simulation, and second, the statement of how many times do the simulation. You might wonder, like, why do they call that B? And it comes from the word bootstrap, which is it's something statisticians, it's just terminology statisticians had around simulations. So basically, running that over in RStudio, and out it comes. So you can do as many simulations as you like. I don't recommend like asking to do 100 billion of them, because then you would really gum up the server, but 10,000 of them is no problem. It only takes a flash, you see. When there's not many people using the server, it can do a lot. And each time you run it, you'll get a different number here, but it'll be small.
I'm getting an error. Can you scroll back so I can look at it really quickly?
How about if I stop sharing and you share, and we'll just nail down this error?
Let's do it.
Yeah. Now on the final quiz, you won't be doing any R, you'll be looking at output,
Right.
but be prepared. Like, what if I were to give you some output that had this warning in it? Like, I might ask you, was this really good idea to do? And you would have to like look at that and check it out.
Okay.
So I'm looking at I see your problem. You see how there's the little stop sign at line 201?
Yes.
Do you see how there's not a comma at the end? Yeah, so you always need commas between your arguments.
Okay.
Now it pops out. And so you got your graph in one window, and if you push the little R console window, you'd have your output to look at.
And then it's perfect. Okay, thank you so much.
Excellent, thanks. I totally advocate for everyone to follow McKinsey's model and just pipe up with these questions and share those screens, because we got time to work this stuff out. Okay, so back to the solutions. So I'd better share the screen again. And so our last one was about the COVID-19 in China. And here they only give you summary data. It's not in a data set. And we're wondering, like, is there a relationship between how old you are and whether or not you die from COVID-19? And so that's actually could be thought of as two categorical variables. If you put people in age groups, which is how the data was presented to me on the web in the spring when I was looking at this, there's like these three age groups. And so that turns age into a categorical variable, a categorical ordinal variable, three age groups. And then the other variable is the outcome, and that's a categorical nominal, died or recovered. And you got this little two-way table. And the first thing you had to do was to find like what percentage of patients in each age group died. And so people were fine with that. They just took the number who died divided by the number in the group times 100 to make it a percent. And the under 70s died only about 1.24% of the time. The 70 to 80s died 8% of the time, and the over 80 died 14% of the time. And so again, I stress this data is like it's correct data, but it's data from way back and towards the beginning of the year 2020 in China. And the doctors like hadn't confronted COVID before, and they hadn't come up with a lot of the cool treatments that they now have. I mean, COVID is still super dangerous, but they've cut down on these death rates considerably, doctors have, by, I think it's like they don't put people on ventilators right away. They have these like tricks about rolling people over onto their stomach, and that kind of helps the breathing. And there's like these plasma treatments that they give people in certain conditions. There's all these tricks that they've come up with. And the other thing that they've kind of figured out, it's not exactly age that puts you at more risk. It's specific conditions that are often associated with age. So like a high blood pressure, that's one of the really big risks. So when you're young, you're very much at risk. If you have high blood pressure and you get COVID, that's really dangerous, just like you're old. But the problem is that old people are more likely to have developed the high blood pressure than young people. And there's some other very specific conditions. Again, I'm no doctor, I'm nowhere close, but it appears to be like how vulnerable your blood vessels are to getting shredded by small clots. That seems to be like the unifying factor right now. And so there's certain conditions like high blood pressure and diabetes and some other things that make your blood vessels more likely to get shredded up by the action of COVID. But there's other stuff about like your immune system and like whether it makes a bad decision about when to kick in certain antibodies. So that it's all very complicated and interesting in a morbid sort of way. Anyway, so but just looking at this time, you have this question. At this time in China, was there a relationship out there in the population, not just in the people that got put into this study here, between age group and outcome? Well, this time, since it's summary data, you have to use some R in a fancy way to construct the little table that you can feed into chi-square test GC. So you'll never have to do this for yourself on a final, like it would be done for you. But you can actually just put a two-way table into chi-square test GC and it'll work with it. And so it spits back the table at you. But it also spits back what table you would have expected to see if the null were right. And so you can look for differences, and like the differences are huge. And the chi-square statistic basically summarizes how huge those differences are. It's a really big number. If the null was right, you could expect it to be around 2, but it's like 1,779. So the chances of getting something so big, if the null is right, are, as it says, basically 0. You're supposed to use this output to assess the strength of evidence provided by the data for a relationship between age and outcome. So there are still some people out there who only talked about what was in the sample. They were only talking about these percentages and how different they were. They weren't going in and saying, hey, if there's no relation in the population, there's essentially no chance of seeing such big differences as what we saw in our sample. So they weren't doing the inferential part. It really all turns, at some point, it's going to turn on talking about the p-value. And so I write a little paragraph where I kind of summarize all that I learned from the chi-square test output and got down to the p-value being about 0, rejecting my null hypothesis of no relationship and my simple conclusion. So what I'm really aiming for is for y'all to be able to go from something like this to something like this without having it like broken down for you in these little spoon-sized pieces like in the earlier questions. So I hope that for the final you can aim to get to this kind of stage. Would there be further questions on the 6.4 DA?
I have a quick question.
Yeah.
So if the chi-square statistic, if it was like 7, I forget, how do we find out if it's like because you have like give or take some for chance of error? How would we find that? Like if
The
it,
give or take figure?
yeah.
So that's buried back in the slides for section 6.3. And
Okay.
it says that if the null is right, then the standard deviation for the chi-square is the square root of twice the degrees of freedom.
Square root.
Yeah, it's on one of the slides. Evidently, it must not be like a big feature of the course because like it's not coming up in the DAs much at all. So I kind of threw it in there just for fun. But for fun, do the square root of twice 2.
So just be like 2 times 2 and then
Yeah.
the square root of it, so it'd be 2.
So
So
it's
it
back to
could be
2. Yeah. And so
okay. So
like,
the answer could be 4 or like 0.
yeah, like you could expect anything from 0 to 4. The 6895 rule doesn't really apply to the chi-square variables because they're so skewed. They don't look like normal random variables. But it's still the case that you would expect to get about the degrees of freedom, give or take a few of these standard deviations or so. You know,
Okay.
so
Thank you.
like
Yeah.
I would still be surprised to see more than like say 6 above the 2. I'd be surprised to see more than 3 standard deviations above that 2.
Got it.
And I'm seeing like almost 1,000 standard
Yeah.
deviations above the 2. And so it's one of those cases where what you see in the data is just so ridiculously convincing that you almost feel like you don't even have to do the inference. Okay, I will stop sharing the screen and end this recording.